My name is Ford Ramsey, and I'm an assistant professor in the Department of Agriculture and Applied Economics at Virginia Tech. And I'm going to be talking about this paper, Impact of Climate on Quantity and Quality of Virginia-type Peanuts. This paper was written with Maria Belota, who's also at Virginia Tech in the School of Plant and Environmental Sciences, and Jesse Tack, who's in the Department of Agricultural Economics at Kansas State University. Our main research question is, what is the impact of warming temperatures on revenue of Virginia-type peanuts? And what distinguishes this paper from many other climate change impact studies in agriculture is that we consider the impact of warming on quality as well as crop quality or yield. And this is important for any estimate of revenue when revenue or price depends on the quality of the crop, and that's certainly the case for Virginia-type peanuts. Studies that do not consider the impact of warming on quality can severely misstate the impact of projected warming on crop revenue. Along with those estimates of the impact of warming on revenue in Virginia-type peanuts, we also look at the ability of breeders to offset negative revenue impacts by breeding for increased yield and quality. The data for this study mainly come from the Multi-State Peanut Variety and Quality Evaluation Program. And this program evaluates different varieties of Virginia-type peanuts. We have data from 1985 to 2017. We have 12 locations where the peanuts were grown over this period. They're all in Virginia, North Carolina, and South Carolina. There are a total of 424 varieties or lines that are observed in the data, and just over 8,000 observations. Some of the locations in the data did not have a weather station either at that location or in all years. So we take our weather data from the PRISM program at Oregon State University. And the PRISM program uses measurements of weather at weather stations, interpolates those measurements and downscales, and ultimately you get measures of maximum and minimum temperature and precipitation daily at a 2.5-mile grid of the continental United States. Now we take the PRISM measurements and convert to daily average temperature using this method that's been used in the agricultural economics literature. So at the end of the day, what we have are measures, just over 8,000 observations of peanut yield and peanut quality, as well as weather variables across the growing season. So this map shows the 12 locations that we have, and you can see that it runs from the Tidewater region of Virginia all the way down to the South Carolina low country. So we get a lot of variation in growing conditions in each year, which is useful for identifying the effect of heat on yield and quality. If we look at the summary statistics, and so this is across the whole sample, all 8,000 observations, we see that the mean yield was 4,346 pounds per acre. There was a lot of variation in this, from a minimum of 263 to almost 8,000 pounds per acre. And then we also have measurements of total sound mature kernels and extra large kernels, as these are the quality metrics that we measure in this paper. And you can see that total sound mature kernels, the mean percentage of the sample is 71%, or just over 71%, and roughly 41% are extra large kernels. I also include summary statistics for the weather variables. The way that weather enters this model, as I'll show in a couple slides, is in cumulative degree days over the growing season. And there are 3 different categories. So in this case, low would be the cumulative degree days between 0 degrees Celsius and 14 degrees Celsius over the growing season. High is the cumulative degree days above 34 degrees Celsius. And so you can see that obviously those very high temperatures are observed much less in the data, but still we do get some temperatures above 34 degrees Celsius. This plot shows all 8,000 observations over the 1985 to 2017. And this just shows the trend in yields over that period. And it should be pretty obvious that over time, we have seen a big increase in yields, especially in 2017, the last year. We have a big bump in yields. So this is the model that we use. And you can see that we're modeling 3 responses. So Y would be the yield. In TSMK is net total sound mature kernels. So it's total sound mature kernels minus ELK. And ELK is, of course, the extra large kernels. And the regression models include an intercept term. It includes gamma subscript I, and that's an intercept term that varies by location. Then we have an intercept term that varies by variety. The G function is just a trend function, and F function is what I'll call the climate function. And so that relates the climate variables in the model to either the yield or the quality metrics. In our case, the climate function is linear. It's just a linear function of precipitation, the low degree days category, a medium degree days category, and a high degree days category. And by including the temperature in as these 3 degree day variables, what that actually allows is for a nonlinear relationship between temperature and yield or ELK or NTSMK. This system is estimated jointly, so the error terms on the far right are all assumed to be distributed multivariate normal. I'm not going to spend too much time talking about the weather coefficients, the coefficients in that climate function, but we find the following in terms of the general effects of weather. And this is incidentally why it's important to include weather in a specification like this so you can get nonlinear impacts, because we find that there's a slightly negative impact of the low temperatures category, of course, a positive impact of the medium temperatures category, but a large negative impact of extremely high temperatures, which is what, in general, what we would expect. Those effects are similar across both yield and ELK. So whenever you have extremely high temperatures, you get really negative impacts on yield and ELK. The impacts of the high temperatures are not as extreme on net total sound mature kernels. And that's because when you have high temperatures, of course, some of that portion of the sample that was ELK is going to fall down into the NTSMK category. But in general, we find what we would expect, which are negative impacts of high temperatures. Now, here's the economics of this. We have a revenue function. So revenue is just price times quantity, right? But in this case, for Virginia type peanuts, that price depends on the quality attributes, which I collect in this vector M. Now, we don't observe prices from buying points, But we do have the calculation that's used by the Commodity Credit Corporation to perform price support values. And that's what we're using here. We put that function in terms of ELK, net total sound mature kernels, and ordinary kernels. From this, the change in revenue from a change in warming can be given by the total derivative of the revenue function. And those parameters of the revenue function are identified from our system of equations that I showed on the previous slide. So basically what we want to do is we're going to have the observed weather, which is weather old, and then we're going to have weather under 1 degree or 2 degree Celsius warming. And we're going to look at what's the change in yield, what's the change in ELK, what's the change in TSMK, and ultimately, what's the change in revenue. So we find the following revenue impacts from quantity and quality. So the way to read this table is that at 1 Celsius, we have a negative 9.35% change in revenue that is attributed to a decline in yield or decline in quality. We have a negative 0.03% change that's attributable to decline in TSMK, and so on. And so what you can see is that the total change to revenue from 1 degree Celsius warming is about 10 to 11%. The vast majority comes from quantity, but there are also negative impacts in terms of quality. We look across a number of different specifications, and this negative 11 to negative 10% change in revenue from 1 Celsius warming is robust to many different types of specifications, as well as choices of the cutoff point for that high temperature category. Now I want to briefly talk about technological change. What this shows, each of those points is the genetic contribution to yield of a specific variety or line, and they're plotted over the year that they first entered the trials. And so you can see that over time we've seen improvement in the genetic contribution to yield. And if you look at that genetic change between 1985 and 2017, there's been enough improvement in yield and quality to offset about a 12% loss in revenue. So if we had the same growth in yields and quality as what we've seen over the past roughly 35 years, we would offset warming at 1 degree Celsius. But obviously we would not offset any warming at higher degree scenarios. So there are 3 main findings in this. The first is that the estimated impact of 1 Celsius warming is roughly negative 10.5 and 11%. That estimate's robust. Most of the impact of warming is through yield, but there are also negative impacts on quality. So if we were to only consider the impact on yield, we would basically understate the total negative impact on revenue. And continued work in breeding has the potential to offset the impacts of warming. So that suggests that we do need continued effort and investment in public and private breeding. Further research will investigate alternative weather specifications and other measures of quality. Thank you.